Good afternoon, everyone, and welcome back to AP Physics 2 for the last unit of review. Today we're starting magnetism. That's Unit 5 for those of you keeping score at home. This is it. This is the last 4 days. So without further ado, here we go as we talk about magnetic permeability, magnetic dipole moment, magnetic fields, and forces. As always, we'll do a quick lesson overview, let you know the direction that this lesson is going to take. We'll do our daily warm-up where we pick up where we left off yesterday. We'll talk through what you need to know to be successful with magnetic forces and fields. We'll work through some guided practice, some released questions from the College Board. We'll do a debrief and summary, talk through what we just did, and then we'll leave you with an AP exam practice for tomorrow. I am Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. Let's take a look at our roadmap real quick to show you where we stand. We are starting the first lesson of magnetism today, and we've got 3 more after this. Anything back behind that you see, fluids, thermo, electrostatics, and circuits, you can still find those videos on YouTube and touch up a little bit of your knowledge in those subjects as well. But as far as today's lesson is concerned, we'll start with magnetism, specifically the causes of magnetism. We'll talk about magnetic domains, magnetic properties of materials, and magnetization of different materials.
And then we'll talk about the magnetic forces experienced by a moving charge as it moves through a magnetic field, specifically why charges experience forces at all. We'll calculate the magnetic force and talk about how that equation is built, talk about the direction of the magnetic force, throw up our right hands and use that, and then we'll talk about the paths that particles follow in a magnetic field.
And by the end of the lesson today, we want you to be able to use force magnetic is equal to QV cross B to determine the magnitude and direction of force magnetic.
All right, so here are the skills that we'll be working on today. We'll be creating representations and models, and we'll be using representation models to analyze situations qualitatively and quantitatively. So here is the warm-up question from yesterday. Here's circuit 1, here's circuit 2. The only difference is that circuit 1 has a switch where circuit 2 has a capacitor. In circuit 2, there's a capacitor where the switch is in circuit 1. Okay, so initially the switch T is closed. In circuit 1, can you describe what happens to those lights? Well, when you close the switch, the lights turn on. They have the same brightness, they're identical bulbs, they're in series, same brightness, same current, same power output. They're bulbs, they're in series. You've got this. Switch S is now closed. What happens to the brightness? Well, switch S has no resistance. A closed switch presents no resistance to current flow. So when the current gets to that junction, so all of the current that's in the line with S and in the line with B, the current in S flows really well. The current in B stops flowing once that switch is closed. You might say that current leaving bulb A decides where it wants to go. There's less resistance in the path of switch S, so it goes that way. However you wanted to get there, once that S closes, B just turns off. What happens to A though? Well, when the resistance of the circuit decreases, because there's no longer a bulb B, when the total resistance decreases, the current that's going through bulb A goes through at a higher rate. Okay, so why does the brightness change once switch S is closed? If the current decreases, if the resistance decreases, the current increases. The potential difference across bulb A increases to equal the potential difference of those batteries. What's actually going on inside that light bulb is that charges are giving up their electric potential energy, and the resistor is converting that into thermal energy. It's heating up, the tungsten filament is glowing. You should be able to discuss those things in terms of different levels of zoom. Either the bulb is getting brighter, or you can talk about electric potential energy and light energy. Or you can talk about individual charges and what they're doing. Remember, one of the central goals of being an AP Physics 2 student is explaining how microscopic effects have macroscopic causes. All right, so in circuit number 2, switch T is closed at time equals 0 seconds. Describe what you would observe over the course of 1 minute. Well, I see a capacitor, so I know that time is going to be important. When that switch is first closed, the capacitor is uncharged. It's really easy to stick electrons to the bottom plate of that capacitor or to pull electrons off the top plate of that capacitor. So once that switch is closed, bulb A lights right up. Bulb B is initially off. The capacitor is becoming charged over time. Within the first moments that that capacitor is charging, bulb B is getting brighter as the potential difference across the capacitor increases, or as the capacitor becomes charged, or as less current flows to and from the capacitor, however you feel like expressing that. The total resistance of the circuit, though, is increasing. As more current flows through bulb B, the total resistance of the circuit is increasing. That's a little bit counterintuitive, but that means that bulb A gets dimmer and bulb B gets brighter. All right. So what does the capacitor act like a short time after the switch is closed, and what does it act like a long time after the switch is closed? Well, the moment that switch is closed, the capacitor isn't slowing the current at all. At that very first moment, there's plenty of room on the plates of that capacitor. Negative charges can get jammed in there without repelling each other, and negative charges can get yanked off the positive plate without electron holes pulling back on them, or positive charges pulling back on those electrons, if that's how you want to picture it. So right after the switch is closed, a short time after the switch is closed, the capacitor acts like a short circuit or a wire or an empty capacitor. But a long time after that switch is closed, the capacitor acts like a broken wire or an open switch. It's already charged. There's nothing else that the battery can do. All right, so after a long time, switch T is opened. Now explain what you would see over the course of a minute. Well, charge has been separated on that capacitor. That capacitor is storing electric potential energy. On the plates of that capacitor are a lot of electrons that want to get away from each other. On the other plate of that capacitor, there's a lot of positive charge, which is attracting other negative charge. So electrons do what electrons do. They flow away from other electrons. They flow towards positive charge. At first, bulb B is kind of bright, and then bulb B gets dimmer. So you close the switch, bulb A immediately goes out. You open switch T, bulb A immediately goes out. There's nothing else applying a potential difference across bulb A. Bulb B, however, remains lit but becomes dimmer over time. The current through bulb B decreases over time as the potential difference across the plates of that capacitor goes down. Remember, charge flows until they're at the same potential. All right. What does the capacitor act like once that switch is opened? You could sort of say that the capacitor momentarily is acting like a battery. It's a voltage source, but not a great one because it's only separated a little bit of charge, and once that charge flows, the capacitor is back in equilibrium, back in its uncharged state. Remember, in order for consistent current flow, there needs to be a constant potential difference, just like for the continuous flow of a fluid, there needs to be a pressure difference. For the continuous flow of heat energy, there needs to be a sustained temperature difference. Batteries and generators and outlets, those things provide continuous voltage difference, constant potential difference. Things like capacitors or even a bolt of lightning, there's a momentary potential difference, but not something sustainable. Okay, here's Mr. Eden with what you need to know.
All right, to be successful on the AP exam this year, you need to know about magnetism. So specifically, magnetism is caused by moving charges or dipoles. Magnetic domains become aligned by an external magnetic field, or sometimes spontaneously. Magnetic domains have their own internal magnetic field, forming a continuous loop. And ferromagnetic, diamagnetic, and paramagnetic materials and the differences between them and the similarities between them as well. Magnetic force on a moving charge, we'll dive into that towards the end of the lesson. So specifically, moving charges experiencing forces while they're inside someone else's magnetic field. And force magnetic is equal to QV cross B. And we'll go over the corresponding right-hand rule that goes along with that as well, just as a really good refresher to get you ready for the AP exam. And the direction of the magnetic force in relationship to the velocity vector when charges are moving through somebody else's magnetic field. So most of today is dedicated not only to what is magnetism, but we are still talking about right-hand rule and how the force is applied to a charge that's moving through a magnetic field. Okay, so first off, we will dive into causes of magnetism, and specifically that matter has this property called magnetic permeability. And you know it as the constant mu naught, and you probably first off had the question, well, where did they get that number from? It didn't just fall out of thin air and just magically appear in somebody's lab notebook. It's just that missing constant that made all the numbers work out perfectly. Now, free space, basically free space is free space. A vacuum has a constant value of the permeability that appears in physical relationships. But free space and matter are two different things. Matter has a permeability value that's different than that of free space. So the mu naught that you see in front of you, that's the permeability of free space, which is 4 times 10 to the negative 7 Tesla meters per amp. Mr. Mancino, did you have something that you wanted to add?
I believe there is something missing from that. Isn't there a pi missing from that? We'll back to you on that as I add that back in.
There is a pi missing from that.
I think we missed a pi. Hi everyone, just one moment. There we go. For those of you screenshotting, you can screenshot that. 4 pi times 10 to the negative 7 Tesla meters per amp. If you took a screenshot a moment ago, please delete that. Sometimes there are typos on the screen. We do try to go back and address those. This is a lot of letters to type for one lesson.
Yeah, and the moving on, the keyboard is broken, so there you go.
All righty, Mr. Eaton, take it away.
Okay, so we also have this thing called a magnetic dipole moment, and it's a fundamental source of magnetic behavior of matter, and it's an intrinsic property, which means it's special to each type of material. And some fundamental particles, such as the electron. And when dipole moments become aligned within a system, let's say you've got a clump of matter that has lots of little electrons around every single atom inside of that material. When those become aligned, those dipole moments are aligned, what you get is either a permanent or an induced magnetism within that material. And what that means is you can make something become magnetic, or it could already be magnetic because of the material itself. So, if a dipole is placed in a magnetic field, though, what does it do? Well, if it's inside of a magnetic field that's pointing in a certain direction, aka the magnetic field vector, what it wants to do is align with that magnetic field vector nice and parallel to that magnetic field. So in other words, if I have a magnetic field that's pointing north, my material that has magnetic dipoles, all of those dipoles want to align to the north direction. They would try to point in the exact same direction. But a compass needle, what's a compass needle made out of? It's probably some sort of permanent magnetic dipole material. And why does it work the way that it does? Well, it's trying its best to align with the Earth's magnetic field. So that's why it points to, we'll get into that next lesson. I'm not going to get into that right now. But you can also take iron filings, and you can put iron filings around a bar magnet. You probably did this in class at some point. Iron filings aren't necessarily magnetized, but when they get around another magnet, the dipoles inside of iron filings, well, they want to align with the magnetic field of the bar magnet as well, and you get what's called an induced magnetic dipole. Now, all magnets also produce a magnetic field. That's kind of an important fact to know, and you probably remember what those fields look like around magnets or magnetic objects. But more specifically, I said this a couple of times already, the Earth itself has a magnetic field as well. It's an important fact to know going forwards and kind of applying that to a couple of different situations that we'll talk about in just a little while.
Okay, so that was a lot to take in. Here's what we meant about magnetic dipoles and magnetic dipole moment. For reasons beyond the scope of this course, electrons have a property called spin. Are they really spinning in the classical sense? Maybe. In the literal sense, maybe not. But it's called spin. You're going to have to bear with us on that. Physicists are not great at naming things. Regardless, the electrons in an atom, due to their motion, create a magnetic field. A magnetic field is a vector field. So magnetic field at any given point is a vector. Because we love naming things, one end of that magnetic field is called the north end. The other end is called the south end. Sure, your teacher probably talked all about maps and the North Pole being a south magnetic pole. Physics teachers love to talk about that. Anyhow, this is a picture of a single atom, or a single collection of very small charges that are all in motion, the result of that motion being the magnetic field that you see, where there is a north end and there is a definite south end. But when enough of these get together in certain kinds of materials called ferromagnetic materials, in a ferromagnetic materials, those individual magnetic spins between individual atoms, they tend to line up. Atoms do what their neighbors are doing. They influence each other. They affect each other. And in a region that you see enclosed in that dotted line, in a region of several particles doing the same thing, or whole bunches of particles doing the same thing, we call that region a magnetic domain. A magnetic domain is a region inside of an object made of a ferromagnetic material where a bunch of the magnetic dipole moments line up. The atoms line up, and they make a magnetic domain. In those materials, a bunch of those domains tend to line up. Oh yeah, so hang on, let me do that again. One atom becomes aligned with a group of atoms. Those domains are represented by the dotted lines in the next diagram. So there's one domain in the middle. There are several domains on the right side of your screen. So from left to right, we are progressively zooming out. That is that this highlighted area here is actually that one right there. So let's highlight that and unhighlight the other one. You'll notice that those magnetic domains are mostly lined up. In ferromagnetic materials, even though the domains aren't perfectly aligned, they're aligned-ish. So get enough of these north-south domains together across an entire object made of a ferromagnetic material, and those north-south domains line up. This is a diagram of a bar magnet. In a bar magnet, many magnetic domains line up, yielding a north pole and a south pole of the magnet itself. So this diagram is not drawn to scale. There'd be a bajillion of these things. Remember, they're composed of bajillions of atoms making a bajillion magnetic domains, but it's a diagram. What are you going to do? The classic question that I ask when I teach students of younger grades is, what do you think happens if you break a magnet? What would the ends be like where the magnet is broken? Well, you are smart AP Physics students. You know that if we break a magnet, we end up with two magnets. If a magnet breaks, each part becomes a bar magnet with its own north pole and its own south pole. And there's why. Because a magnet is composed of magnetic domains that all individually have north-south poles. Okay, Notice the title of this slide. Please don't screenshot this. AP Physics 2 is not a course about vocabulary. It's definitely not a course about vocabulary. You can't make flashcards for this course. But anyhow, I thought that I would put up these definitions. It says don't screenshot. Ferromagnetic materials can become permanently magnetized by an external field. Heat up an iron nail and put it near a strong magnet and cool it off, and you've got a permanent magnet. Paramagnetic materials can be temporarily magnetized in the presence of another magnetic field. All materials, water, copper, things you wouldn't think of as magnetic, have a property called diamagnetism. And diamagnetism means they are feebly, weakly repelled by a magnetic field. You can repel anything with a strong enough magnetic field. So even though you wouldn't think of water as magnetic, water does exhibit diamagnetism, which is super weird. Okay, you can screenshot this next page because here's what I did for those of you who really want to learn vocab. Ferromagnetic materials can be permanently magnetized by an external field. Paramagnetic materials can be temporarily magnetized. Diamagnetism means everything is weakly repelled by a magnetic field. If you feel the need to screenshot that one.
All right, this is my favorite part when we start talking about charges actually moving through a field. So in terms of magnetic force on a moving charge, we know a small amount of moving charge creates a small magnetic dipole. And a region of moving charge altogether creates a magnetic domain. So if you have multiple moving charges, that becomes a magnetic domain. Now, when we talk about that being a magnetic domain, that means this is evidence that moving charges affect magnetic fields. And if moving charges affect magnetic fields, do magnetic fields affect moving charges as well? I think that's what Newton's third law actually states. So charge affects field, field affects charge in some manner, some way. Now,
Just a note, folks, you're going to be taking an AP test in a few weeks on May 13th. If you would like to make a Newton's third law argument, regardless of what your teacher uses in the classroom, maybe just type Newton's third law. Try not to use abbreviations like N3L. I see that a lot when I'm reading tests, and not everyone knows what you mean by N3L. If you have a special name for things in your classroom, that's a great shorthand to use with your teacher. If you're going to make a Newton's third law argument, maybe just write third law. We know whose law it is. You can say the third law, but please write a little bit more detail than N3L.
Yeah, that's good advice. The magnetic force that a charge experiences has to depend on the quantity of the charge in terms of coulombs, how many coulombs of charge you have, the speed of the charge in terms of meters per second, and the magnitude of the magnetic fields, which is in terms of Tesla, and how perpendicular velocity and magnetic field actually are. So maybe you remember seeing a sine theta components, and back in the lesson overview and what you need to know, we said that force magnetic is equal to QV cross B. And we'll talk about that cross in just a few moments, but the quantity of the charge is represented by, you guessed it, it has to be Q. That's everything we've ever talked about with charge. And the speed of the charge, we don't use S.
If I may, Mr. Eden, do remember that the quantity of charge can be positive. It can be negative, and that means that positive and negative charges are affected differently. If Q is positive or if Q is negative, there's a difference. We'll talk about what that difference is shortly. But this is evidence of Newton's third law. If something exhibits a force on a charge, the charge exerts a force on the something.
All right, and we also know that the speed of the charge is represented by velocity. So there's your velocity vector that you see on the screen. And velocity is a vector, so I care about the direction of that velocity, and that direction actually shows up in our cross term when that turns into a sine theta. Now, the magnitude of the magnetic field is represented by a capital B, which is the strength of the magnetic field in terms of Tesla. And notice that that is a vector as well. We put a vector symbol above that. So again, I definitely care about the direction of the magnetic field. Now, how perpendicular V and B are, well, that's where the sine theta comes into play. So what do you remember about what sine of 90 degrees is? Well, sine of 90 degrees gives you 1, right? So if your angle between velocity and magnetic field is 90 degrees, your sine theta term typically falls out of the equation. And more than likely, you probably did lots of practice problems with this exact thing in class, and you really kind of never worried about the sine theta portion. But the sine theta comes into play very, very, very importantly later on when we start working a little bit more advanced problems, and we start seeing a helical pattern of the charge when it's moving through a magnetic field. You may kind of remember what that looks like as well. So
Certainly, and anyone
yeah, go ahead.
who's coming to us from AP Physics 1, if you took AP Physics 1 before this, you remember that sine theta is a measure of how perpendicular things are. The most perpendicular things can be means they have a sine of 1. The least perpendicular that things can be, well, a sine is 0 if two things are parallel. Just like cosine is a measure of parallelness. If something has a cosine value of 0, that's the least parallel that things can be. That's when they're perpendicular. When the cosine is 1, that's the most parallel that things can be.
There you go. So on your formula chart, this is what you would find pretty much typed exactly as you see it on the screen. So force magnetic, which is a vector, is equal to Q velocity, which is a vector as well, and it's crossed with B, which is also a vector. Now, this second line, that's actually the way that you would see it written on your formula chart. And it's kind of just a reminder that the cross product between QV and B is actually sine theta. And again, that's the measure of how perpendicular those two objects were. Whereas, like Mr. Mancino just said, the cosine is how parallel those things are. And you saw that with work when you tried to push a box across the floor. You want the force and the displacement to be in the same direction. You want them to be parallel to each other to get the most work done on the object. But in this case, to get the most magnetic force, you want the angle between the velocity and the magnetic field to be as close to 90 degrees as you can possibly get it to achieve the most amount of magnetic force.
Now that cross product term, that little X in the first line between V and B, that's math nerd secret code for the right-hand rule. There is a very specific relationship. That's not just multiplication. That X carries a lot of meaning to it. And when we wrote this equation sheet, there's a lot packed into that X. It's correct, but it doesn't help you determine the direction of force using your right-hand rule. So your teacher has already taught you a right-hand rule that works. Use that right-hand rule. Mr. Eaton and I discussed whether we should talk about the right-hand rule with you, and we decided briefly. The first equation, here's what it means. And here's the way I do the right-hand rule. If you learned it a different way, that's great. Good for you. Keep up that way. The way I explain it to my students is you take these 3 fingers and you make the letter M for Mancino or for magnet, and you make that little M. And then this index finger points in the direction of velocity or current. So M for magnet, index finger for velocity. Your thumb points in the direction of the resulting force. This particular hand shape is the cross product of 2 vectors. This one's in the positive direction, this one's in the positive direction, this one's in the positive direction. That's what the right-hand rule cross product means. Your teacher taught it a different way, and that's great. Keep doing it that way. You may have had the press, you may have had something else going on, and that's great. Do it your way. On the bottom, that's the magnitude of the magnetic force. QVB sine theta is always the magnitude. If you're really good at right-hand rule, or if you don't know what a cross product even is, just use this, use that. Because there is no restriction on this, because we're expecting this to be an open note test, If you know that under the stressful tick-tock of the clock, you forget which vector is velocity and magnetic field and force, and you're just sitting doing this for a while, write it on your hand. If you know that you're going to encounter a magnetic force question, and after all, this is AP Physics 2, write what you need to write on your hand. Okay, here we go. Let's see if you learned something about the importance of the direction of the magnetic force and the velocity. Or this is a trick question. An object with a positive charge passes by one end of a bar magnet. Oh, look, the velocity's down. Maybe that matters. The magnet exerts an inward force on the object. What is the direction of the force exerted by the object on the magnet? The magnet exerts an inward force on the object. What is the direction of the force exerted by the object? Oh, that's a Newton's third law question. Always be ready. No one ever expects Newton's third law to show up in a magnetism question, but it's perfectly likely to happen. Newton's third law says, if the magnet exerts an inward force, the object exerts an outward force. Oh, pardon me, my mistake. Alrighty. So here is a region of magnetic field. I didn't specify what the direction was. We're going to be talking about some changes that can happen in this particular interaction. Here is a charge heading into that region of magnetic field and moving in a circular path. Magnetic force. Oh, Mr. Eaton, this one's all you.
So magnetic force, which acts perpendicular to a particle's velocity, just like Mr. Mancino just showed us with his right-hand rule, and I actually kind of might use that with my students now. I've never noticed that that makes an M. That's kind of fun. Now,
It's
it
for
cannot make a
Mancino.
particle. Sure. So it can't make a particle speed up or slow down, and maybe you've heard that already, but that would be something that I would write down. Now, we know from dealing with electric field, that electric field is the only way to actually speed up an object or to slow it down. But what that means is if the magnetic force is not able to speed up or slow down a moving charge, that really means that a magnetic field cannot do work on a moving charge. And you may remember from physics 1, there's another situation where there was a particular type of force that didn't do work on the object. And I bet you it's something that was moving in a circle, okay? You probably did like the little stopper lab where you swung a stopper above your head and inevitably you probably hit yourself in the head or something like that. I hope it didn't happen, but it always happens, so don't feel
Oh,
bad.
that is the best part of that lab.
Yeah, and the key is to pull down on the string to get it to stop, so whatever. Okay, anyway, the magnetic force causes a charged particle to move in a circle. Really, that's what we're going to be talking about for the next 15 minutes or so. So on your screen, you see a formula that says QVB is equal to mv squared over r. And really what this is we started with Newton's second law, which was net force is equal to ma. The net force is QVB, which is magnetic force. And that has to equal ma centripetal because that object is moving in a circle. And you probably remember a very fancy little substitution that the centripetal acceleration is actually v squared over r. I believe all that information is still on your formula chart for physics 2, but if it's not, I would jot this down somewhere. This type of problem shows up a lot, but we're not going to be calculating with it. Really what we're going to be doing is discussing what happens when you change one of those variables, change the magnitude of one of those variables. How does that affect the speed, or how does it affect the radius of the circular path, so on and so forth. Now, honestly, 9 times out of 10, what you're going to want to do with this type of equation is you'll probably solve for the radius of that circular path, specifically because we just talked about how magnetic force doesn't do work on the object. It can't speed it up or slow it down. It just causes it to move, guess what, in a circle. And you'll probably be asked, how does the mass, changing the mass, affect the radius of the circle? How does the speed change the radius of the circle? How does the charge and how does the magnetic field affect the radius of the circle? So this solution, well, I guess it's a solution for the radius. This is a really important thing to have with you, or at least know how to derive it quickly on the fly. And again, I wouldn't put it on a note card per se, but I would practice getting from QVB is equal to mv squared over r to r is equal to mv over qb. All right, so here's that same charge that Mr. Mancino already showed you. It's in a region of certain magnetic field and it initially curves upwards. So what's going to happen to the charge if it had an opposite sign? So where is the sign of the charge actually located? I think that's with the Q, and it's on bottom of the fraction for R is equal to NV over QB. What do you think is going to happen? I think it's going to curve the opposite direction. Instead of curving upwards, it's going to curve downwards instead. And I don't know, does this animate for it to curve downwards?
It does not. So the
Okay.
idea is we are going to present you with a bunch of changes. Here's one path. And we're going to present a bunch of questions. What would happen if the object were of a different sign? What would happen if the magnetic field pointed the other way? We have no idea what's coming up on the test on May 13th specifically, but we do know that typically the College Board has asked a lot of questions about the behavior of a moving charge in a region of magnetic field. We tried to grab all of them, every which way they've asked this question, every which way it could be asked, so that as you go through this review, you can ask yourself, well, what would happen if the charge were of the opposite sign? It would flip the other way. How about this one?
What if it was moving faster? So take a look at what you wrote down. It was probably R equals MV over QB. If V is larger, what needs to happen to the radius of the circle? If you answered larger, that is correct. What about slower? Well, that would just be the opposite. If it's moving slower, you would have a smaller radius. How about heavier? So more mass. Well, that has the same effect as velocity does. If you have more mass, you'll have a larger radius. It's harder for the magnetic field to make the charge curve upwards. So the radius is just a little bit larger. If you doubled your mass, your radius would be double. So what about if you had more charge, more Q? Where is Q located in the equation that you wrote down for this? So Q is on the bottom of the fraction. And if Q is larger, that means that R would be smaller. You would have a smaller radius for the circle. Now, what about a weaker field? That's on bottom of the fraction too. So if you had a smaller B, that means that you would have a larger radius as well. How about an opposite direction field? So as long as everything else was still the same, if the field was in the opposite direction, your curve would not go up, it would go down. All right, what about traveling in the direction of the field points? I feel like Mr. Mancino is trying to trick you. He wrote this one.
I am full of trickery. How would the path be different if the particle were traveling in the same direction that the magnetic field points? If the particle's velocity were exactly parallel to the direction of the magnetic field?
So that means the angle is 0. What sign is 0?
The sign of 0 is 0. If this were traveling directly parallel with the magnetic field direction, it would just travel on through and not curve. But what if this particle were traveling in the opposite direction of the magnetic field? If the particle's velocity is from the left side of your screen to the right side of the screen, and the magnetic field points from the right side to the left side, how would the path change then? Well, what's the sine of 180 degrees? It's also 0. There would be no magnetic force. Okay. So, as a particle travels through a magnetic field, this is not the question that I intended to ask in this particular spot. That's very strange. Well, a particle travels through a magnetic field from the left side of this shaded region to the right side. Now there's a point P that's been kind of covered up by these arrows. So first of all, in each case, the particle goes from where you see it enter on the left side to point P. And let's say this particle has a positive charge. So the question is, what is the direction of the magnetic field inside the shaded region? If the particle has a positive charge and enters on the left and exits on the right, but lower, what is the direction of the field? Well, for a positive charge to experience a downward force, that means that use whatever right-hand rule you like. The result you get should be that the magnetic field is outwards, is towards you, the viewer. But which of these four paths would that charge take? The top left path is a straight line. The top right path is a continuous curve from where the charge enters to point P. The bottom left path is a curve while the charge is in the magnetic field, and then a straight line when it's no longer in the magnetic field. And on the bottom right is a straight line and then another straight line angled at point P. Well, of course, we know that the magnetic force curves the particle's path. And then when there's no magnetic force, that particle should follow Newton's first law and keep on moving in a straight line with constant velocity because there is no external force. Alrighty, time for some guided practice. Take it away, Mr. Eden.
Here we go. As usual, 3 questions. And guess what? All 3 questions are about magnetic force on a moving charge.
Appropriately.
It's exciting. I love it. Okay, so here you're given a diagram that shows that there's a positive charge moving to the right with a speed of v naught, and it enters a region of constant magnetic field B directed into the page, something that we didn't review with you, but when you see X's, you know that that's kind of like the back of an arrow sticking into a target. That's the fletching. And so that's the arrow pointing into the page. Just remind yourself that, and when you see dots, well, hopefully you remember that dots means that the field is out of the page. Now this field is directed into the page. The charge is coming in from the left-hand side, and you are expected to find the initial direction and the magnitude of the acceleration of the particle as it enters the magnetic field. So what's the initial direction of the acceleration? Well, Newton's second law says that a net force should cause an acceleration on a massive particle, and we're assuming that this particle has mass as well. So I think you need to find the direction of the force. So use your right-hand rule to determine which direction the force is. So on the screen, I've given you the right-hand rule is used for force magnetic is equal to QV cross B. And the way I teach my students is I say point the index finger along QV. I just kind of point along QV, so that needs to go to the right. And your middle finger or your 3 fingers, like Mr. Mancini showed you, needs to be pointing into the field. Therefore, your force is upwards. And I apologize to you, I did not solve this for acceleration for you, but if you'd like to try that, we might be able to give you the answer to that tomorrow.
Well, you should know that according to Newton's second law, A equals F over M. And I think you've got enough here to say, if F is QVB and the mass is M, the acceleration might be QVB over M.
There you go. All right, so now we have a charged object with a net charge of positive 10 millicoulombs, and it moves perpendicular to a uniform magnetic field of 5 Tesla. The force exerted on the object by the magnetic field is 0.5 newtons. What's the magnitude of the velocity? And notice on this one, they gave you the force this time, and you just need to find a different component that's inside of your magnetic force equation. So as usual, you probably need to start with force magnetic is QV cross B. And again, this is kind of mathy. Don't expect that. We need to know what's going to happen when you change one of the variables to that magnetic force. But let's go ahead and dive into this one. We can talk about that in just a second if we have time. So rearrange this for B before you do anything else. So B is force magnetic over QB. That leaves my velocity by itself. And I just plug in what I'm given inside the problem, and I get a velocity of 10 meters per second.
And certainly you're unlikely to encounter a question that asks you to calculate things, but certainly The College Board might ask you, well, what's the effect of doubling the strength of the magnetic field? Or what's the effect of doubling the velocity? So being able to discuss how changes in the properties of the situation affect changes in the magnetic force, that's great. You're not going to have to calculate the magnetic force. You might not even need a calculator.
There you go. All right, last one for you. Each of the figures below shows the path of a charged particle moving in the plane of a page in a magnetic field that's perpendicular. Pop quiz, which way is the magnetic field? It's into the page. If the mass and speed and charge of the particles is the same, in which case does the field have the greatest magnitude? So looking at your equation for magnetic force, you know it's QV cross B, and what it's saying is which one has the greatest B value, the greatest magnetic field strength in terms of Tesla. So if I have a larger force, because the B is larger, because Q and V are all the same, and so is mass, it's probably the one that has the greatest force. And if you remember talking earlier about a greater force, how does that affect the radius of the circle? Is it going to have a big wide radius, or is it going to have a really small tight radius? Think about it for just a second and we'll show you what the answer is. All right, let's do it. Hopefully that's the one that you picked. So the greatest magnitude of magnetic field is going to give you the smallest radius as long as all of those charges have the same mass, charge, and speed.
So we're hoping that somewhere on a sticky note, on a piece of paper somewhere, you have written down the rearrangement that the radius of a charged particle as it travels through a magnetic field, the radius of that path is mv over qb. That relationship shows up an awful lot on the AP Physics 2 exam. The interaction between a magnetic field and a moving charge causes the charge to move in a circular path. And different properties of that situation affect the radius of the path. However, nothing in that interaction between the magnetic field and the motion of the charge affects the velocity of that charge. Affecting the velocity is done by a different sort of field, and we'll be talking about interactions with that field coming up. So you've done it again. Congratulations. One more day down. A quick debrief and summary for you. Key takeaways for today is that a charged object has to be in motion and in the presence of an external magnetic field to experience magnetic force. And there's a lot to this next one. If the velocity of a charged object is perpendicular to the magnetic field, the resulting motion is circular, with the magnetic force pointing towards the center of that circular path. You can use Newton's second law to determine the radius of the path and use that relationship to figure out how changes in the situation affect the radius, which depends on mass, velocity, magnitude of charge, and the strength of the magnetic field.
And can you answer these challenge questions? Why do mass coronal ejections from the sun have a corkscrew shape? If you don't know what those look like, Google that really quick. There's some pretty neat images out there. And why are most electrical and data cables shielded? The packages say shielded on it.
All right. As usual, here is an AP exam practice question for you to screenshot and for us to discuss tomorrow. If you're doing these and you're keeping up with the practice that we outlined on AP Classroom, you are in a very, very good place. Well, you're here watching the live stream, so you're already in a pretty great place. Here is page 1 out of 1. See, it's a one-page question today. Grab a screenshot of this, and we will discuss it next session. So get your screenshot. Now you've got me with my thumb up in a screenshot. Thank you very much for watching, everybody. We hope that you'll join us again tomorrow as we discuss more about magnetic force on a wire, magnetic force between current carrying wires. We have a lot to look forward to. It's been a blast teaching you about magnetic forces.
Thanks again. We'll see you tomorrow.